Sine waves, an extremely useful tool in math, in engineering, in computer science. Today, let's take a look at the very fundamentals of a sine wave. Let's try to understand some of its properties, as well as how we can actually generate a sine wave. You're watching another Random Wednesday episode on 0612 TV. Hello and welcome back to another Random Wednesday episode. Now, today's video isn't going to be an extremely long one. We're just going to try and understand the fundamentals of, what a sine wave actually is and what are some of the properties it actually exhibits. Once we're done with that, we'll move on to take a look at a formula that we can use to generate a sine wave. Once that's done, we'll actually move over to Python and try to implement that formula. So yeah, that's basically what we're going to be doing today. Without any further ado, let's jump into understanding the fundamentals. So before we can actually discuss anything meaningful about sine waves, let's first try to understand what a wave actually is. Well, here's the deal. A wave could look something like this. And in fact, it could represent a plethora of different concepts. One common usage of waves is to actually show how a quantity changes over time. In such a scenario, the horizontal axis is actually time. And so you can imagine that this changing quantity is perhaps at one particular fixed position in space, and what we're plotting out here is how that changes over time. Of course, that's just one way of looking at things. We can also use a wave to represent one moment in time. If we do that, then the horizontal axis becomes position. What this means is we're actually looking at an area of space at one moment in time. What you see here can also be called a snapshot of a wave, because, well, that's essentially like taking a picture of a wave in space. The reason why we use waves to express ourselves is because, well, it happens to be a great model for a lot of physical phenomena that happens around us. One prime example is sound. Sound is just, air particles vibrating over time. And in fact, if we were to actually look at any one bit of air particle, its vibrations over time can be plotted out as a wave like this. So yeah, that's what a wave is. Let's now actually home in on sine waves and try to understand what they actually are. Now, here's the deal. What you're seeing on screen is a sine wave. A sine wave has this very typical look. It is made up of a smooth segment that goes up and down and is repeated multiple times. Sine waves, and in fact waves in general, tend to carry these three properties. First and simplest of all is amplitude. Amplitude simply refers to how tall the wave actually is. Amplitude tends to be associated with strength. And what that means is, if we're talking about sound here, then the greater the amplitude, the louder the volume. In terms of light, the greater the amplitude, the greater the light intensity. So, in this particular case, if we were to actually increase the amplitude of the wave, you would expect it to be stretched vertically. On a similar note, if we were to actually decrease the amplitude, it would be lower. And in fact, if we were to decrease it all the way, it becomes zero. And in fact, the wave has been reduced to a flat line. So that was the amplitude. Let's now move on. The next thing we could look at is frequency. As mentioned earlier, waves tend to be, one simple pattern that is repeated many times over. And for waves or segments of waves in which, this can be clearly defined, we can actually count how many such repetitions occur in a second, and that value is the frequency. In this particular case, if the amount of wave you see on screen happens to be collected over a second, then this is a 4 Hz wave, and we say that because this simple pattern has repeated itself 4 times over, within the space of a second. If we were to actually double the frequency of the wave, as you can see, it appears to be squashed horizontally. If this region is still 1 second, this is now an 8 Hz wave. simply because that cycle has now been repeated 8 times over. Similarly, a lower frequency version of this wave will be stretched out horizontally. Since there are only 2 repetitions here over the space of 1 second, this is a 2 Hz wave. In terms of light, different frequencies actually represent different colors, whereas in terms of sound, different frequencies actually correspond to different pitches of sounds, with higher frequencies corresponding to higher pitches. Let us move on to the last of the 3 properties. Now, in this case, we're looking at a sine wave, and we start a sine wave at, the 0, we go up, we go down, and we return to the 0. But here's the deal. If we were to start this wave at any other point, well, it's still a sine wave, just somewhat shifted. And this, in fact, is one of the properties, known as the phase. The phase of the wave is in fact measured in degrees, and it is generally expressed as an offset from, the 0, the original starting position. Now, in case this isn't clear, let's take a look at this demonstration. Now, this is a sine wave that you know and you're very familiar with, starting at the 0, and that is why we call this phase 0 degrees. Now, if we were to actually scoot this wave such that it starts a little bit ahead, somewhere in between the peak and the 0, well, that's called 45 degrees. Scoot it forward a little bit more at the peak, that's called 90 degrees. I think you can see where this is going. If we move forward again in another 45 degree increments, we end up halfway between the peak and the 0 point. Like so. I think you get the rest of the picture here. A 180 degree phase is the same as actually inverting the original wave. Of course, an inversion refers to flipping it about the vertical axis. So yeah, as you can imagine, it is just opposite to the original wave. So moving forward through the next few 45 degree increments, you can see that essentially we're just offsetting the wave more and more, until we end up right back where we've begun. When we start at the first 0 again, well, the phase has actually returned to 0 degrees. So yeah, that has been the concept of phase, and to think of it simply, it just refers to the starting point of the wave. So that has been the 3 fundamental properties of a sine wave. Now, for the rest of this episode, let's imagine that we are dealing with sound. Of course, as mentioned earlier, sine waves can be used to represent, many different types of physical phenomena, but let's just sort of limit it to sound, and, that should be enough to give us a general understanding. So yeah, with that in mind, let's actually talk about generating a sine wave. In particular, let's talk about generating a particular tone, a particular sound that has a fixed length and a fixed frequency. Something that we can actually generate and play back. How will we do something like that? So let us begin by taking a look at some of the math that goes into generating sine waves. Of course, the first thing you need is the sine function. In this case, we're going to label the horizontal axis t because, well, in a lot of cases it stands for time, so it makes sense. By supplying a changing value to the sine function, the value of course goes up and down, creating the iconic sine shape. However, we have next to no control over this. In fact, the amplitude is locked to ±1, and the frequency also cannot be changed. In fact, what's happening is, well, as the parameter increases, that's what's drawing out the sine wave, and what we end up getting is, well, complete cycles whenever we actually clock enough to represent one full rotation. If we're going to express this in degrees, then, well, the degrees are shown on screen. These are of course multiples of 360 degrees, which represents a full rotation. As an aside, a lot of the time when we're talking about trigonometric functions like sine, we tend to actually use the radians measurement instead. You've probably seen this, but in case you haven't, the idea is this. Radians are simply a different way to express angles. We start off at 0 just like degrees, and at the 90 degree position, that angle is equivalent to half pi of a radian. At 180 degrees, we have pi radians. At 270 degrees, we have 1.5 pi radians. And of course, a full revolution, 360 degrees, is equivalent to 2 pi radians. Since many programming languages actually make use of radians instead of degrees, we're going to be actually expressing everything in terms of radians for the rest of this episode. So, going back to the sine wave we've seen earlier, what is known as the period of the wave would be 2 pi. And that is, well, we get one complete cycle every time t actually increases by 2 pi. If we were to actually write out the numbers, well, we'll realize that this actually represents an extremely low frequency sine wave, especially if t is in seconds. What we're seeing here means that it actually takes about 6.3 seconds to actually complete one cycle of the sine wave, and that would represent an absolutely inaudible sound. Let's find out how we can actually solve this problem. Now, when we actually say sine t, we get a wave like this. When we actually multiply t by a number, what we're doing is we're squashing the wave horizontally. This of course corresponds to an increase in frequency, and of course the larger the number, the more squashed it's going to be, or in other words, the higher the frequency gets. Now, before we do anything, let us actually multiply it by something to get things on a common ground. Since by default, each cycle actually takes 2 pi amount of time, multiplying 2 pi into the sine function actually makes the cycles complete within 1 second. This makes things much easier to manage. Since we have a 1 second interval, we can easily scale this to whatever frequency we like. And that is indeed what we're gonna do. By further multiplying the inside of the sine function by f, we can actually now set the frequency of the sine wave. So that's our first parameter, the frequency. Let's move on to our next parameter. Now, here's the deal. If we were to just use the function as it is, what you realize of course is that our sine wave starts from 0 and after a cycle ends at 0. But here's the deal. By adding a small number to the inside of the sine function, what we're doing is we're actually asking the function to start at a later point. And that in fact corresponds to the concept of phase. In fact, by adding different values to the sine function, well, we are actually changing the phase in radians. This can be expressed using a variable called phi. So yeah, there you go, that's another parameter taken care of. And of course, the last one of the three is amplitude. This is extremely simple. By actually just multiplying the entire sine function by a factor, well, you actually stretch it vertically, and that either makes the sound louder or softer, depending of course on the value you're actually multiplying everything by. So all that's left to do now is to actually implement what we've just understood. Basically what we're going to be doing is we're going to be generating a sine tone and then exporting it to a wave file so we can play it back. That's the idea. Let's jump right into putting this in action. Now, before we begin with actually writing code to generate a digital sine wave, you have to understand one thing about computers, and that is the fact that a continuous sine wave cannot actually be represented properly on a computer. Instead, we're gonna have to make do with samples, and that is actually taking note of the value of the wave at different points in time. Essentially, what we're generating is an array of amplitudes that changes over time. So yeah, with this concept in mind, let us actually jump in to start writing Python code. For this video, we're actually going to be using two different libraries, namely NumPy and SciPy. NumPy is going to be used for array manipulation. You're going to see how convenient it is, whereas SciPy is just going to be used to produce the wave file. You can of course replace this part with whatever library you like. Depending on what you choose, you can even play back the sound as it is. So the first thing we want to do is to simply port over our formula, from math to Python. But of course, this isn't going to be working on its own. I mean, we need to figure out what t actually is. And not only that, we'll also have to actually load up our results into an array that actually holds all the samples. So first and foremost, let's try to understand something about, the nature of that data. And let's start with how large that array should be. that is actually dependent on two pieces of information. Firstly, how long you actually want the sound to be in seconds, as well as its sampling rate. This refers to how many samples we actually want to have per second of sound, and one common value that is used is 44.1 kHz. Now, I'm not going to talk too much about how to select a sample rate. I've already done a video about this in the past that goes into a lot of detail. So yeah, if you're interested, do click on the annotation link on screen. If you're not going to go there, then let's stick to this value of 44.1 kHz. So of course, we'll have to update our function a little bit so that it now takes in a length as well as the sampling rate. The next order of business is of course to actually generate all the samples. Depending on what programming language you're using, you'll probably be using a loop. However, I've chosen Python here because Python has this cool feature that doesn't require a loop. So let's take a look at how this method works. All we have to do is to actually generate an array of input values. These values are then fed into the sine function, and that gives us our wave. Now, this might be a little bit hard to understand, so let's actually, break down this particular statement and try to understand what we're actually creating. The arange function, which is part of NumPy, actually generates an array of increasing numbers. The start point of the numbers in this array is your first parameter, and the end point is your last. You can optionally specify a step size, which refers to the size of the increments between each number in this array. Now, in order to see why this works in our current application, we're gonna have to, sort of plug in some sample values to figure it out. Here's the deal. Let's assume that we want a sampling rate of 10, an unusually small number, but let's just go with it. And for the sake of simplicity, we want the length of our wave to be 1 second. What this means is this arange function call will run from 0 to 1, taking steps of 0.1 per item. This creates an array of 10 items, starting at 0.0, and increasing as you would expect. Our next order of business is to of course feed this value into the sine function. But first, let's say we want the frequency to be 1, and for there to be no phase shifting at all. What we get at the end of the day is of course one full cycle of a sine wave. Of course, strictly speaking, we're only going to be getting 10 values out of this computation because we've only put in 10 input values. This sine function is going to operate on all 10 values and of course give us 10 results. So hopefully this makes things a little bit clearer. All we're doing is we're coming up with all the little intermediate values that will be used to plot our sine wave. Of course, in case you're not actually using Python and you cannot actually, just construct an input array and stick it in there, you can of course use a loop. Instead of generating this array, all you have to do is use a for loop to basically generate all the numbers that you will find in this array. Using a loop, just repeatedly call the sine function. Every call will give you one of the results. All you have to do then is to load those values into your output array. The length of your output array is the length of the audio multiplied by the number of samples per second. So if we go on to complete our script, essentially all we have left to do is to actually call the function we've just created, and by supplying all the information that is needed, we'll actually get back a wave that fits our specifications. Since I'm using SciPy in this case, all I have to do is to use the write function in the wave file module, and that will actually produce, the wave. This is then written to a wave file on disk, and of course you can play it back to hear your sine wave. And there you have it. Today we've learned what a sine wave actually is, what its properties are. We've then moved on to taking a look at a formula that can be used to generate a sine wave. And finally, we've actually made our own sine wave using Python coding. That's all there is for this episode. I hope you've gained some insight today. But that's it. Thank you very much for watching, and until next time, you're watching 0612 TV. Thank you very much for watching. If you liked this video, consider checking out the rest of my work on my channel. Alternatively, you may be interested in a playlist of my earlier work on computing and computer science topics. If you'd like to show me some monetary support, I am on Patreon. You can find a link to my campaign in the video description. Of course, you can simply like this video or leave a comment. I'll be sure to respond as soon as I can. To keep in touch with my future uploads, do subscribe to this channel. And for even more updates, check out the official Twitter account for this channel at 0612TV. Thank you for your support.